Welcome to Gen.Struct.2 and Lateral Forces, Lesson 2 quiz, question number 3. And it says, steel girders are efficient bending members because, and it gives A, B, C, D. And I will say that steel girders are efficient bending members because, remember, their shape looks like this, and it uses the moment of inertia the most efficiently, because you have your neutral axis, and it gets that with a thinner web. It allows those flanges to get further and further out, and that makes it a more efficient use of your materials, as opposed if you use the same amount of material, amount of steel, and it's in a block like this. This is a much more efficient beam than this block that has the same assumed areas. These areas are equal. Alright. So let's continue on here. And these are relatively stiff as well. Alright. So let's start with A. A, they have great shear strength. And that is a negative because we're talking about bending. Bending is not shear. Alright. I think it's that simple. Most of their material is in the flanges. And that seems correct, because most of the material is in the flanges, and the flanges are further out. I think that's a pretty good answer. So that means they have a higher I, and if you'll remember, your stress and bending, M equals M over S, or MC, or MY over I, depending on what you want to call that. So I is part of that, and the further out you have those material on the flanges, and since the flanges are further out, the better I you have, because I equals 4 rectangular shapes equals BH cubed over 12 plus AD squared. And the more you do this equation right here to find I, and you will do this, but the more you do this, this equation is I plus AD squared. And a better way to write it would be the sum of I plus the sum of AD squared equals the sum of your parts, I guess is what I'm trying to say, and that's why I'm writing this sum. Alright, so as you can see, but you could say, well, some people will just say, oh, BH cubed over 12. BH cubed over 12, that's what I equals. But that's not the true story. You'll see that these flanges, the BH cubed is going to be really small. The BH cubed of this web is good, right? Because you have a high H. You have a big H. Oh yeah, that H is huge. That'll give us good I. But when you look at AD squared, this AD, and this doesn't have to be D, you could call it something else. It's the distance from the centroid, let me change colors here so you can see what I'm doing, the centroid of the web to the neutral axis. And that's 0. So for the web, AD squared equals 0. But let's see real quick, comparatively, what, we can't do that because I don't have any numbers. But run some numbers, check this out yourself, and just say, hey, well, let's see what the BH cube, let's say this is a 12-inch flange, which is a decent sized flange. 1 inch, that's a real thick flange. Alright, so this BH cubed over 12 is going to be base equals what? 12 inches times the height equals 1 inch cubed over 12. So that's going to be what? 1 inch to the 4th. Okay, 12, yeah, that makes sense. Now let's look at AD squared. The area is 12 inches squared, 12 times 1. And D equals, let's say, well, it depends how big your D is. Let's say we have a very, 72-inch web, which this would probably be, if this is a 72-inch web, let's say it's a 60-inch web. Okay, so 30 inches to the top, plus it's 30.5 is your D. D equals this. So that's the centroid. Some people show it like this. The centroid of that is 30.5 inches. That's gross. Let's try it again. 30.5 inches. So let's run a quick. What's AD squared of that flange? So AD squared equals the area, which is 12 inches squared, times D, which is what we said, 30.5 inches squared. And I'm going to have to get my calculator out for that. And that gets you 11,163 inches to the fourth. And yes, you can say, well, that's got to be wrong. No, it's completely and utterly right. To the fourth. Sorry, I had to put that back. So this is infinitely larger than 1. So let's figure out what of the web. And obviously, since you have 2 of these, you're going to double that. You have this web down here, and that's going to, that 80 squared. And that's why I meant the sum. So you're going to have the I plus 80 squared for the web, the I plus 80 squared of the top flange, and the I plus 80 squared of the bottom flange. Or since it's rectangular, it's BH cubed over 12 is your I. All right, so it'd be 2 times this, and that's what you can see. Hey, that's getting an incredible amount away. So that's why most of their material is in the flanges. And I don't like that. I think there would be a better way to say it, because that's not necessarily true. You can have a huge web and a smaller flange, but so you could say, well, no, not most of their material is in the flanges. And that's why I don't like that, because I deal with a lot of plate girders and whatnot, and I come across a lot where this, if you're coming across a plate girder with a railroad bridge or whatnot, and you'll have a really tall web. It may be 3/8 inch, but the fact that it's 72 inches tall and these are 20 inches, it can double that. And so you might have more material in that web. So I don't like that answer, but I think I see where they're getting, and I think that's the answer. So I'll write most likely. Yes. Okay. So let's and I know I'm kind of going around about this, and you probably don't need all this information, but I think it is important. So what I'm going to also do is say, okay, so that's what you're getting from the flange is 1 plus 11,163. So that's 11,164, and that's times 2 because you have 2. So let's see what the I plus 80 squared of that web is. So let's just call it I web equals BH cubed over, so base equals, let's say it's a 1 inch web. Let's say it's 1 inch times, so we said 60. And it's a reasonable. I think this might, if 60 inches, you probably have a little bit larger flange typically. But once again, this isn't perfect. I just came up with it real quick. Base is 1 inch, and your height is 60 inches. Wait. Yes, that's what we want to do. Over 12 plus a. Let's go ahead and figure that out. I don't want to confuse you, so I'll go ahead and calculate it. Which is A is going to be 60 inches squared. D is going to be 0. So this is going to go to 0. I didn't want to simplify that. So as you can see, that the eye of this web is actually pretty large, but you'll see that it doesn't compare to what those flanges are from the 80 squared. So I is 1 times 60 2/3 divided by 12. Well, that's actually pretty high. It's a lot higher than I thought it would be. 18,000 inches to the fourth. So actually it is larger than one of those flanges, that eye of that web. But it also is, if you look at what the area is, right here we're doing 12 inches, and that's 60 inches. So that's 3 times, what's 60 divided by 12? It's 5 times the area, and it's almost 1.5 times the effective I. So from the two flanges, you're having 24 inches. Now I'm going through this quick, so you try to stick with me. So A flanges, this is both flanges, is 2 times 12 inches squared equals 24 inches in both flanges. And you're getting 22, I might be getting this math wrong, 326, let's say, or 328 inches. So, but this is how much, I hope you're understanding what I'm trying to do here. Using the 24 inches of steel area, you're getting an I of 22,328. Over here with the web, using an area of 60 inches squared, you're getting only 18,000. So that's 2/5 of, using 2/5 of the area, you're actually getting more I. So that's being more efficient with your material. All right. I hope that wasn't confusing. I'm going to move on. That was a bit lengthy. All right. C, their modulus of elasticity is high. And if you go back to this equation right here, you will see that modulus of elasticity has nothing to do with strength. It does have to do with your deflection. So, and you know, maybe you don't know, but for a uniform, and this is the equation I'll use most of the time, is uniformly distributed load, and it's like 384 EI. And as you can see, that E, it does account for it. So that's a deflection, though. So yes, that takes some truth, but I don't think that's what they're getting at. And then D, they have a tapered profile. Yeah, that could help, but I don't think it's the right answer. So I'm going with B as your right answer. Let's switch it back and see if they agree with me. We have what? Question number 3. B, since most of the material of a steel beam or girder is in the flanges at a maximum possible distance from the neutral axis, it has a large section modulus and therefore is an efficient bending member. And that's correct. I said moment of inertia, but section modulus equals I over C, or I over Y, however you like to represent that. So I and S are very, very, very highly correlated. They're pretty much the same thing, but not exactly. And I'll leave it at that. All right, now we'll see you on question number 4. I hope all this explanation helped. If not, I apologize, but oh well.